All right, guys, we're going to talk about parametrics today. Parametric equations introduce a third variable, but you don't graph it in 3 dimensions. So here's an example of where it's useful in the real world. For example, this talks about the number of wolves in a certain, it says on an island, given over the number of years. And here's the number of rabbits over the same number of years. And you'll see that as the number of wolves increases, the number of rabbits decrease. But we can also graph those in terms of rabbits and wolves, where you get this cyclical shape, okay? And you plot those with the third variable time being t, and I'll show you how that works. So here's another example where at this is the vertical distance something travels. This is the horizontal distance that something travels as you throw an object or shoot an object off or whatever. And then this is the physical distance as horizontal this way and vertical this way. Okay? So when we talk about, I'm going to throw a ball up and it's going to come down, the ball goes straight up and straight down. But when we talk about its height, it makes this shape. If we were to throw the ball with a forward momentum or project an object at an angle, then it moves forward in a constant rate. And this is the combination of those two things. So the parametric equations determine the object at a certain time. You can find both its horizontal and vertical components. The variable t in this case, which is time, is called a parameter. The graph is plotted over a set period of time. So this one is from 0 to 4 seconds. Okay. And you can indicate orientation because the graph is going to go in one direction or the other as time passes. So those are not in your notes. That was just an intro. Here's the top of your notes worksheet. It says parametric equations are used to describe the horizontal and vertical components of an equation. Parameters are arbitrary values, usually time or angle measurement. Parametric equations can be used to graph non-functions because we can have things that go back in time, like the cyclical picture of the wolf and rabbit population. That's not a function because it fails the vertical line test. It says if f and g are continuous functions on the time interval or the interval t, then the set of ordered pairs f of t, comma g of t represent a parametric curve. Okay, so in your examples on your worksheet, it says sketch the curve given by this set of parametric equations. For the x value, you're going to say -3 plus 4t. For the y value, you're going to say t squared plus 3. Now, this is very important when you go to graph it on your calculator. It's going to have t values only from -3 to 4. It would include decimals and fractions and everything in between there. But to get a nice smooth curve on our graph paper, we're just going to graph the integers. What we do then is we write down the t values and we plug them to find the x. We're going to do -3 plus 4t. So if we multiply this by 4, we get -12 minus 3 is -15. This multiplied by 4 would be -8 minus 3 would be -11. -4 and a -3 would be -7. This would be -3. Put in a 1, you'd get 4. Minus 3 is 1. 2 would be 8. Minus 3 is 5. 12 minus 3 is 9. And 16 minus 3 is 13. I hope I did those right. Then to find the y values, we're supposed to take the t and square it and add 3 from this rule right up here. So we're going to not use the x's, okay? We're using these values and plugging them in here. So 9 plus 3 is 12. -2 squared is 4, plus 3 is 7. 1 plus 3 is 4. 0 plus 3 is 3. 1 squared is still 1 plus 3 is 4. 2, 4 plus 3 is 7. 9 plus 3 is 12. And 4 times 4 is 16 plus 3 is 19. All right, we're going to plot these, but we're going to plot them carefully using only the x and y, not the t. And we're going to watch as the smooth curve develops and indicate orientation or put arrows on it. So we start at negative 15, 12. I think that's here. And then we go to negative 11, 7. So we're going this way. And then we go to negative 7, 4. And negative 3, 3. One, 4. 5, 7, and it's not required that you put a arrow between each dot. 9, 12. And finally 13, 19. All right, I'm having trouble seeing these straight, so I hope that's right. Now, these don't have arrows on the end. Kind of like vectors, they have direction or orientation, it's called here, but it has endpoints as well. The endpoints come from when t is negative 3 and when t is positive 4. So when we had a t of negative 3, we have an endpoint here. And when we had a t of 4, we have an endpoint here. So the endpoints were at negative 15, positive 12, and positive 13, 19. Now, I will tell you when you do these in your calculator in a minute, the calculator doesn't let you set a particular window only in terms of, it doesn't stop on the table, but it will stop on the graph, I believe is what I'm trying to say here. All right. They can be used to represent graphs that are not functions. So sometimes it will look like this or something, meaning it fails the vertical line test. Okay. Now we're also going to talk about what's called eliminating a parameter. So we're going to, it says to convert a rectangular form, you can solve either of the parametric equations first. And then what I've done here is I got the t by itself here. If you do this t, it says it's okay, but you have to remember a plus or minus when you square root. If we just solve for this t, we don't have that problem. So we add 2 over to the other side. Then we divide by 4. Now we have the t all by itself, and then we put that in here. So we end up with y equals x plus 2 over 4 quantity squared plus 1. Now, you could leave it like that as far as I'm concerned, but if you were writing this as a vertex form parabola, you would square the top and just get x plus 2 squared. But when you square the denominator, you get a 16, and if you pull that out front, it's a 1/16. Okay? So this is vertex form. The vertex of our parabola was at negative 2, 1, which should make sense. Did I just, oh, was this not the same problem, or was it? I don't think this was the same problem, was it? Was that just an example? Add 3, divide by 4. Did I add 3 and divide by 4? No, this was just an example. All right. before I finish with this one though, you could also do the form we were just doing in conics, where you would subtract the 1 over here. And then take and get rid of the 1/16 by multiplying a 16 over here. This form would also be okay. And sometimes it's easier to get that form, and especially when some of these are going to open sideways. So either that form or this form is fine. We're going to go back now and do the one that we did up above, number 1. So this time we're adding 3, and then we're going to divide by 4, and then we're going to get, now that the t is by itself, I'm going to put it into the other one. So it'll say, we're squaring it, so the x plus 3 is squared, the denominator squared becomes a 16, and then there was a plus 3 on the back, okay? Or I could have said x plus 3 over 4 squared. I would take that as well. And then if you wanted to, you could move the 3 over to the other side. And multiply the 16 onto the other side. And that is in the conic form that we learned, where we have 4p equal, or 4p times y minus k equals x minus h quantity squared. Nitro! Sorry, guys. Sorry guys, I'm making this on a Sunday afternoon and the dogs aren't behaving. Where was I? This was example 1. So the vertex here was at -3, 3. I just wanted to go back to number 1, and hopefully that works for our picture. -3, 3 does indeed look like the vertex, okay? Now, we're going to try another one. And then I'm going to show you how to do it on the calculator. But let's do one more by hand. This one has different definition of t. Okay, it wants the endpoints. You can write it up here. I'm going to write it back here with a little more room. We're going to say t goes from -4 to 4 this time. And for the x's, we're supposed to square it and add 4. T squared plus 4. So square that is 16, plus 4 is 20. Square that is 9, plus 4 is 13. Squared is 4, plus 4 is 8. 1 plus 4 is 5. 2 squared is 4, plus 4 is 8. 9 plus 4 is 13. And 16 plus 4 is 20 again. Okay. Now, to get the y's, we're supposed to divide it by 2 and then subtract 3. Or half t minus 3. Half of that's -2 minus 3 is -5. -1.5 minus 3 would be -4.5. -1 minus 3 is -4. Half of that would be -1/2 minus 3 is -3.5. 0 would be -3. 1/2 minus 3 would be -2.5. Half of 2 is 1 minus 3 is -2. 1.5 minus 3 is -1.5. And half of 4 is 2 minus 3 is -1. All right, now when we plot the ordered pairs, remember we're plotting the x and y only. And let's see, 20, -5. Notice this graph paper is stretched really funny. The scale is counting by 2's here, 2, 4, 6. And I made it count by ones going this way, so it wasn't too scrunched up. Okay, then it goes to 13, which would be here. -4.5 would be down here. So the direction is this way. And then 8 to -4. When you do this on a calculator, you have to kind of watch it graph to find the direction, or trace the points after you've done it. 5, -3.5. 4, -3. And that's when it turns, now goes back this way, I think. 5, -2.5 is up here. So this one is not a function because it just failed the vertical line test. Where am I at? Five, -2.5, 8, -2. There we go. 13, -1.5. And 20, -1. All right, so this is a sideways parabola. We're supposed to find the endpoints, and again, those are given by the two values that t had as its ends. So when we put those in, we got 20, -15. This was an endpoint, and this was an endpoint. Whoops, and it doesn't matter what order you list them. All right, I think then it's going to ask us to eliminate t again, right? Is it going to ask us to go back and do those? I don't know. I'm going to do it anyway. This one I would probably do the eliminate t by getting rid of, or solving here for t, because I don't want to have to take a square root and remember my plus or minus. So I'm going to do y plus 3 equals t over 2, and then I'm going to multiply by 2. Whoops. So t is this entire quantity, or I could distribute it. But then I'm going to put it into x on the other side. So I have x equals 2 times 4 plus 3, or y plus 3. Quantity is squared, add 4. So if I subtract 4 over to the other side, and I square both of these quantities, so I square the 2 and I square the y plus 3. Whoops, where did that squared come from? I don't know. Now I could divide by 4 onto the other side, and I have 1/4 x minus 4. You can leave it like this as far as I'm concerned, guys, but I'm just trying to show you how this ties into the conics that we did right before Christmas. This would be 4p. P is very small. It's 1/16, which is why it's such a narrow parabola. And the vertex is at 4, -3. So 4, -3 right here. And it's a narrow parabola going sideways. Okay. I should have left this one. Well, I didn't do a very good job. I was trying to write it in HK down here, and I didn't. Okay, let me try that one more time. X minus H, and this was Y minus K. So HK, or the center, was at 4, -3. All right, anyway. All right, I'm going to show you how to do it on a calculator. So what you do is you take your calculator and you go to mode. And tomorrow we're going to need degrees, so I went ahead and put it in degrees. Actually, I'm going to do one today on the notes too. But I'm going to show you an example that needs degrees. And then I'm going to go down here, and we learned polar the other day, but now we're going to learn parametric. So instead of function, it needs to be in parametric. Okay? For the one I'm going to do, it wouldn't matter degree or radian, but in a minute I'm going to do one that talks about an angle in degrees, so we would need it in degrees. Now, when you do this and you go to window, you get a t step. Instead of theta here, it asks for t. And the thing is, you have to set t to whatever the question tells you. So I'm going to do the one we just did real fast. Maybe if I can get it to go up. So this one was from -4 to 4, okay? You don't need to do this one with me. You can just watch. And then we're always going to make this t-step something small. 0.1 is what we used in polars, and that's what I would use here as well. I can show you why in a second. And then for the x and y, you could just look at the graph paper. X was -4 to 20 something. Put 22. And the y values on this graph paper went from like -8 to 6 or something. And it's, again, not that important. I'm just trying to make sure the graph fits. Then you go here, and now instead of x and y, it says x in terms of t. And our x in terms of t was t squared plus 4. So when you use this xt theta button, we are now in parametric, so it's going to bring up t. This is dependent on the mode you are in. And it was t squared plus 2. I have no idea what it was. Was that right? T squared plus 4. And when I go down here, it was t over 2 minus 3. And if I graph it, I got what we did a minute ago. And it even stops at our endpoints here. If you go trace, it says when t is -4, here's an endpoint. Now you will notice you cannot trace backwards. You can only trace forward because the only thing you control is t. So as I go from -4 to +4, the t changes, and I'm tracing out ordered pairs. Okay? And I can trace until t is +4, but then I'm done. If I go second trace, I have no choices here. These are all calculus options except for the value. So I could find the value when t is 2, but that's the only thing I'm allowed to do. I cannot trace by x and y. I can only trace forward and backward in terms of t. Now, if I changed my window to something really, really tiny, I'll show you what happens. It takes forever to graph because, what did I change the wrong thing? Doesn't like that window range. See, it goes much slower, okay? And yours may take even longer. Mine's got the power of the computer behind it. But the other option is if you made t really big, like 2, it would only count from 2s from here to here. So it would only put like 4 points. See how it gets all pointy? So we usually leave the t-step 0.1 because that's calculating 10 little dots to connect between each of these integer values. All right, we're going to go to the next one on our paper, which is the one we're supposed to do on the calculator. I wrote a reminder here. It says use the window for all of these that has the t, max, and min from right up here. So ours is going to be 0 and 9. So I'm going window. It wants me to do 0 to 9, and I'm going to leave this step 0.1. And then for the x and y, you just need to go by the graph paper they give. This is like -2 to 8 or something. Yeah, we could leave it -4 to 10. It doesn't matter as long as it fits on the graph paper. And then up and down, it went -3 to 7. I can do exact if that makes you feel better, but and then you have to change the equations. So the equations for this problem are just t over 2. Oops, I should have deleted all that first, cleared it out. And then for y, the equation is square root of t and then a +2 on the outside. Arrow to the right, +2. Okay, it should graph now. And it's a little piece of a parabola or piece of a square root graph. It's only the top half because it was a square root, not a x squared or t squared. And I can go to the table and see my integer values if I wanted to fill them in the table. But see, it does go past the points. We only wanted 0 to 9. So at 0, we had an endpoint of 0, 2. And see, it'll keep going even though your graph doesn't. At 10, we had an endpoint of 5, 5.2. Or was it 9 I was supposed to stop at? No, it was 9. Okay. At 9, I had 4.55. But again, if you go to my graph, you can trace those. Here it says 0, 2 is an endpoint. And then you trace out until it stops and it won't go any further at 9. And at 9 it says 4.55. Okay, let's move that to there. All right. So it was 0, 2, and 4.55. And if you were to go, you have to just watch carefully or list the ordered pairs and plot them to see. I'm actually go arrow to the left and hit enter to turn it off, and then I'm going to hit enter to turn it back on so that I think it'll graph it again to show you. Well, it went really fast, but it goes from left to right. Okay, the ordered pairs are listed here if you want to do some of them. I'm going to go 0, 2, 2, 4, 4.5, 5. That should be enough, right? 0, 2, 2, 4, 4.5, 5. So there's the little piece that was going this way. And that's it. All right. So again, rewrite in rectangular form means get rid of the t, so you only have x's and y's. And it doesn't matter which way. This says y equals. There is, you will notice, no squared or square root. So this one is linear. If we were to solve, they want us to have a y left. So, well, it doesn't matter here. We can do either way. I'm going to do t equals y plus 4. And then I'm going to put it in here. So I have x equals 2, y plus 4, plus 3. And let's see, maybe I'll go ahead and distribute. So this is 11. So if I subtract it over to the other side, I would have x minus 11. And then I'm dividing by 2. So there's the equation of the line we would get. I don't care what form it is. You could have left it like this, unless this one said solve for y. Okay, doesn't look very good. All right, this one I would solve here. Again, because there's no squared, so I would get x minus 5 equals t. And then I would put that in over here. So I'd have y equals -3 and then x minus 5 quantity squared. So that's just a parabola if it's in vertex form. Okay, the h and k are 5 and 0. Or you could rearrange it and get it in the form that we had when we did conics, which would just be multiply 1/3 over here. So we'd have a negative 1/3 y minus 0 equals x minus 5 squared. Either one's fine. Doesn't matter. A summative question that could be on a quiz would ask you simply to find an ordered pair. It says when t is 11, what ordered pair do you get? So you just put 11 in for the x, and that goes in this spot. And then you put 11 in for the y, and that goes in this spot. I'm just trying to show you an example of what they'll ask on a quiz. Really easy. You have 44 minus 2 is 42. If you put the 11 back in here, you get 11 squared plus 1, which is 122. That's a big number, but it just asked you for the ordered pair. And then I'm going to show you one example today of projectile motion, and then tomorrow we're going to do a whole lesson on this, but we're going to do it together for fun. I think there is one on the quiz, but I'm not going to assign a bunch of practice on this on your own. It says parametrics are used to simulate projectile motion for an object launched at an angle. So when it's not launched straight up or straight out, okay, or actually could be straight out, but the horizontal distance can be found using parametrics, and it's x, and this is the equation you have to use. The x value is always t times whatever the initial velocity is, times the cosine of the angle you're launching at. And y is actually, this is the formula, it's negative 1/2 gt squared plus t v sub 0 sine plus h sub 0. And g is the constant. We're going to use all feet in these questions, so we're going to use this one, negative 16 t squared plus t times initial velocity times the sine of the angle it's launched at, plus any initial height. So is it launched from the ground or 5 feet off the ground, or what's happening? This is just another slide. It does show down here that if you happen to be using meters, you'd have negative 4.9 instead of negative 16, but we're going to do all feet, I think. All right, so here's the fun. Luigi's kicking a soccer ball. He kicks the ball with an initial velocity of 35 feet per second. So v sub 0 is 35. At an angle theta of 48 degrees with the horizontal, and when he kicks it, the ball was 2 feet off the ground, so the initial height was 2. So we're going to put all these into the equation. Remember, the x was t times v sub 0 times the cosine of the angle. And remember, x and cosine have a little thing together. They're always together. Y and sine are together. The y is the height, which has to fight against gravity, so it's negative 16 t squared plus t times, again, initial velocity times the sine of the angle it was launched at, and then plus any initial height goes on the back. We're going to put those in our calculator, and we're going to have to fiddle around to make the window work. All right, this video is getting long. I'm going to type as fast as I can here. I already forgot the numbers. Shoot. 35 cosine 48. And then this one is negative 16 t squared plus t times 35 sine of 48. It understands if you don't put the times in there, it knows to multiply, so that's not necessary. Plus 2 on the back. Now, t is time. I don't think I need 9 seconds for a soccer ball to come down, so I can put 9, it won't matter. X is how far the ball goes. If I just do this right now, boop, goes right off the top and away. I need it to be much longer, so actually I can't have negative distance to the how far the ball travels, so I could leave that, but it might go 30, 40, 50 feet, I don't know. I'll put 40. The Y, the ground would be 0, so we really don't need, this is height. We really don't need that much. I'm thinking it goes more than 7. Oh yeah. It goes up. Ooh, look how close I came to the end there. Maybe I'll put 50 here so I can see a little better. But I need to go a lot higher. So, I don't know, maybe I'll do 30 here. Soccer ball doesn't usually go 3 stories up, does it? No, 30 was way too much, but that's fine. If I trace along here, I can see where the ball is at each point in time. So we're going to answer a bunch of questions real quick. This Y could have probably been 20. I think we did 45 or 50 out this way, and 3 seconds was plenty. If you don't put enough T, let me show you what happens. If you set the T too short, like you say 1 second into the story, boop, the ball stops in midair, which doesn't make any sense. Okay, so this 3 seconds was enough for it to hit the ground. And I was going to change this one to a little bit shorter. All right, now I am going to go ahead and answer all the questions. Find the time until the ball hits the ground. So what time is it when it finally gets to the ground over here? And we're not going to get super accurate with these. This is about as close to 0 height as I can get. So it took about 1.7 seconds, and it was about 39.8 feet away. So 1.7 seconds. At this time, the ball will travel about 39.8 feet, or almost 40 feet away. How high did the ball get? Well, the highest the ball got was up here somewhere. So if we trace back in time, try to figure out the highest it ever went. Looks like 12.56 is the highest. Okay. So about 12.6 feet. Will it clear a 6-foot defender that's standing 35 feet away? These are the fun ones. Okay, so if we trace until X is 35 feet away, does that make sense, guys? This distance away is 35. We could get a little bit closer if we tried like putting a smaller value in, like 1.4 something. We could try to get as close to 35 for this as we want. I'm really okay with you leaving it at 1.5 here. That's pretty much 35 feet away. And the ball was 5 feet in the air, so I don't think it cleared a 6-foot defender. If you wanted to try 1.48, 1.49 might be closer to 35 feet away. I was just trying to get this close to exactly 35 feet away. But it definitely is not over 5 feet or over 6 feet. So I'm thinking, no, it didn't clear him. It probably hit him in the face. Okay. So those are the fun things where you can find the path of the ball and where it is at some point in time. We'll do some more of those tomorrow. I hope you like parametrics. Just mostly it's calculator work.